Section 6, Isosceles, Equilateral, and Right Triangles. We're going to talk in this section about some theorems and postulates, but we've actually already covered some of this when we talked about classifying triangles because we had to use some of these ideas to classify. So some of it should be a review. We're just naming what we've already stated. The base angles theorem says if two sides of one triangle, something that's important to think say right now is base angles theorem. We're talking about one triangle. We're not trying to prove that two triangles are congruent to each other like we have been doing. So the base angles theorem says if two sides of one triangle are congruent, then the angles opposite them are congruent. And we've actually already talked about this when we were classifying triangles. The converse of the base angles theorem says that if two angles of a triangle are congruent, then the sides opposite of them are congruent. Again, we've kind of already talked about this. We're just putting a name to the idea that we've already discussed. Corollaries to those theorems. Remember, a corollary is something that follows closely or that you can conclude, and we are not going to have to prove these corollaries. So they're just statements that we can say based on the theorems. It says if a triangle is equilateral, then it is equiangular, and if a triangle is equiangular, then it is equilateral. Again, we've already stated this previously, but now we're just putting a name to, or they actually don't even have names. We're just saying that they follow closely or are corollaries to the base angles theorem. The hypotenuse-leg congruence theorem says if the hypotenuse and a leg of one right triangle is congruent to the hypotenuse and a leg of another triangle, then the triangles are congruent. So in this case, when we're using the hypotenuse leg congruence theorem, we're going back to trying to prove that two different triangles are congruent. And if it's the hypotenuse leg congruence theorem, we have to be talking about a right triangle. So remember, the hypotenuse is the side that is opposite the right angle of a right triangle, and then a right triangle actually has two legs, the two sides that are forming the right angle. The first example says, use the diagram of triangle WXY to prove the base angles theorem. I'm not a huge fan of this because it doesn't actually give you givens. So based on this picture, I'm going to say that our givens are that WX is congruent to XY. Obviously, they each have a tick mark. And XZ is going to bisect WY. And those are givens. And if you notice, it's actually a perpendicular bisector because WZ is perpendicular because it's showing us that we have a right angle formed. If we think about the base angles theorem, we're trying to use, notice that they've split this triangle into two smaller triangles, but we're actually trying to use the larger triangle. The base angles theorem, remember, says that the two sides opposite, or the two angles opposite of the congruent sides are congruent. So we're trying to prove, essentially, that angle W is congruent to angle Y. And to do that, we're going to actually split this and think about this as the two smaller triangles, WXZ and XZY. So if we can prove that the two smaller triangles are congruent, then we can use that statement that we talked about a lot in the last section, that corresponding parts of congruent triangles are congruent. If you notice, if XZ is bisecting WY, we can say that WZ is congruent to ZY because of the definition of bisector. You can also say that XZ is congruent to XZ because of the reflexive property of congruence. And if we have all three of those sides congruent to each other, then we can say that the two triangles are congruent because of the side-side-side congruence theorem. Based off of that, I can now say that angle W is congruent to angle Y because corresponding parts of congruent triangles are congruent, and I have proven the base angles theorem. The next example, we're given two different triangles, notice that are forming a larger third triangle. A asks us to find the value of x, and B asks us to find the value of y. To find the value of x, we're going to be looking at the smaller triangle. Notice that this is an isosceles triangle because it has two congruent sides. And notice that we're given the angle that is not opposite of the two congruent sides. So we're given that third angle. If you remember, the three angles of a triangle add up to 180. We know that that top angle is going to be 50 degrees, and we actually know the two remaining angles have to be equal or congruent because they are opposite of my congruent sides. So to find the value of angle x, I can take 180 and subtract 50, which is that top angle that's not opposite of my congruent sides, which leaves 130 degrees for the two angles that are opposite of the two congruent sides. Notice that x is just one of those angles that is formed, so I need to take 130 and divide it by 2, and when I do that, I get 65. So the measure of angle x is 65 degrees. Then they ask me in B to find the value of y. Well, if you look at the second triangle formed, or the larger triangle formed with angle y, notice it is opposite of a congruent side of that second smaller triangle. We don't have any angle measures given to us of the triangle where y is a degree, or is a measure of a angle. However, if we use the fact that angle x is 65 degrees, notice that it would be supplementary to that to the angle adjacent to it. So I can say that this angle is 115 degrees. Then I can do the same thing that I did to find angle x. I can take 180 minus 115, which is 65, which means that the two congruent angles have a sum of 65. So I need to do 65 divided by 2, which gives me 32.5 degrees for y. This last example, we are given that TS is perpendicular to PS, TS is perpendicular to QS, TS is perpendicular to RS, and TP is congruent to TQ is congruent to TR. That's all of our givens. We're trying to prove that the three triangles formed are congruent. If you notice that since we have so many perpendicular lines, notice that TS is perpendicular. It looks like it's a telephone pole. So TS is going to be perpendicular to essentially the ground. So it's saying SQ, which would be going from the bottom of the telephone pole out to the bottom of this. It's like a tether. If you've seen these towers that have the huge long tethers coming down to make sure that it doesn't like blow over in the wind. That's kind of the picture that we're looking at. But if you notice, all of the sides that it's perpendicular to are actually going to be the sides along the ground. Something that should be popping out to you is that if TS is perpendicular to all of these different lines, TS is going to be forming right angles at all of these different lines, with all of these different lines. So the next step that we should be thinking is saying that all of these triangles that we're trying to prove have the side TS as one of their legs. So we can say that TS is congruent to TS. Then we can say that all of these angles are going to be right angles because they are perpendicular lines. So perpendicular lines form four right angles. We can say that they are right angles. Notice that the last thing we're given is TP is congruent to TQ is congruent to TR. If you thought of this as three different triangles, those would be the hypotenuses, and TS would be one of the legs. So in all three of these triangles, I know that the hypotenuses are congruent and one of the legs is congruent because it's sharing a leg, TS. Because of that, I can go ahead and say that the two triangles are congruent because of the hypotenuse leg congruence theorem. Today's assignment is on page 239. It's numbers 8 through 28 and 33.